Hello students, let us start the class of AEC. In the previous class we have been discussing this common gate configuration of JFETs, and I am showing you the picture as well as the expression for the VDS in this slide. We had already discussed this in the last class. Let us have a brief recap. Here you can see that the gate is grounded and VDD will be much larger than VSS for that matter, which is in comparison with the BJT's common base configuration. And you can see that input is applied at the source and output is taken at the drain. It can be reverse also, because anyhow it is the AC current that is flowing, and whether it is going from drain to source or source to drain does not matter there. Now applying KVL to the whole loop, what we can write is VDD minus IDRD minus VDS minus ISRS plus VSS equals 0. That is because VSS will be having a negative terminal connected to this resistance RS. Now we can simplify this as VDS equals VDD plus VSS minus ID into RD plus RS, because the source current and the drain current are going to be the same. The voltage at the drain with respect to ground can be written as VD equals VDD minus IDRD, because there is only a drop of IDRD across this drain resistor. All the remaining voltage will be from drain to the ground. Similarly, the voltage at the source can be written as minus VSS plus IDRS. That is because the source voltage is at a negative potential and there will be a drop across this particular resistance RS. So VS is minus VSS plus IDRS. Now using all these expressions, we can solve one particular exercise for the common gate configuration. Let us proceed with that. Determine the following for the common gate configuration: VGSQ, IDQ, VD, VG, VS and VDS. Let us try to solve. This is the circuit diagram given for the common gate configuration. Drain resistance is 1.5 kilo ohms, source resistance is 680 ohms, and IDSS is 12 milliampere, VP is minus 6 volts. You can see in the circuit that there is no source voltage as such connected. Even though this is a common gate configuration, VSS is basically 0, we can say. Why? Anyhow, the JFET does not require any gate current for its operation, unlike BJT. In BJT, it was very much essential to connect two power supplies, but in JFET, strictly speaking, we may not require VSS at all, as is evident from this example, because there is no need of any gate current. Only thing is the gate needs to be reverse biased for bringing the JFET to the middle of the transition curve. That is anyhow going to happen because of the connection of RS. This we had seen already in the self bias circuit. Means we simply connect one resistance at the source. So naturally at the gate it will induce a negative potential when we apply KVL to the input loop. So the functionality of the JFET is not going to be affected. It will be in the quiescent condition only. So that way VSS is not actually absolutely necessary. Now using all the expressions which we had derived in the previous slide, let us try to solve this exercise. For the transfer characteristics, VGS equals 0 minus IDRS or VGS equals minus IDRS, as we already know. As we already know from the self-bias circuitry, that we have a line for the gate to source voltage that is nothing but minus IDRS, because here VSS itself is 0. So we can use this for plotting the line that is corresponding to the gate to source voltage. For this equation, the origin is in one point on the load line, while the other point must be determined at some other arbitrary point. and for which we can substitute either IDSS by 2 or IDSS by 4, and we can respectively get VGS. So choosing ID equals 6 milliampere, IDSS by 2, we will get VGS equals minus IDRS, that is equivalent to minus 4.08 volts. Now using this particular value of VGS, we can gradually find out the Q point. Look at this Q point. The transition curve is already plotted, presuming that we already have followed all the procedures for plotting the transition curve. Now using this particular value of VGS, taking origin as well as the other point here at the top, you can see when ID equals 6 milliampere, correspondingly we get VGS equals around minus 4 volts. So using this particular point and this particular point, we draw a line and it cuts the transition curve somewhere here. So that corresponds to the quiescent current is 3.8 milliampere and the quiescent gate to source voltage is minus 2.6 volts. Now using these two, we can actually find out the other values. So the resulting solution is A is VGSQ equals minus 2.6 volts. Then IDQ equals 3.8 volts. These two are directly obtained from the graph. Now let us find out the other values using the equations that we had applied by applying KVL. So see, VD is VDD minus IDRD, that is 12 volts minus ID 3.8 milliampere into 1.5 kilo ohms, we get around 6.3 volts. VG is 0 volts and VS is ID into RS is 3.8 milliampere into 680 ohms, that is 2.58 volts. Why VG is 0 volts? Because gate is directly connected to ground and even the source is connected to ground. There is no VSS there. So naturally VG is 0 volts. VDS is VD minus VS is 6.3 volts minus 2.58 volts, that is 3.72 volts. Now this is the end of the DC analysis of JFET, and this is going to be continued now. In the next part, we will discuss the JFET's small signal model. Just like with the BJT, what we did was initially we had some biasing circuits of BJT and then we performed the DC analysis for those circuits. Gradually we moved on to the AC analysis using the small signal model. In the same way, now I will go to the next slide, there next set of PPTs where we will be discussing the small signal model. I'm just sharing that slide. Yes. Let us discuss the JFET small signal model. You already know what is meant by small signal. Small signal means signal is so small that we presume that when the switch is working in the quiescent point, the influence of the input signal on the quiescent point can be ignored always. The signal is so small enough that we will assume that there will not be any serious non-linearity at the output as such. That is what we presume, and that is why we call it as small signal model. Anyhow, those concepts are going to be repeated slightly here once again. Now you are already familiar with this particular curve where Q point is here. Now this is the transition curve of BJT. I have specifically shown whatever curve I had shown earlier, the same thing I am showing here. But for JFET it is different. It will be VGS and this will be ID. But for the sake of illustration, I have reproduced the same curve which I had used in the first module. Now you can see the input signal is exactly having two cycles, positive as well as negative cycle, which are almost identical. But the output you can see that the positive cycle is slightly larger than the negative cycle. That is because of the nonlinear transfer curve. Now, if Q point is here, we should presume that our signal is so small that it will not introduce this much of non-linearity at the output. That is what is called as faithful amplification. Now, based on this presumption, we will be obtaining the small signal model for the JFET. Now, due to the non-linear operation of the device, the input signal applied can introduce amplitude distortion at the output if the signal is of larger amplitude. Hence, to maintain the response of the amplifier as linear, the applied input signal must be small enough, and such operation is called as small signal operation. We also know that always our input signals are actually in millivolts or microvolts or sometimes nanovolts or picovolts, and even it can be femtovolts, zeptovolts, attovolts, yoctovolts. It can be right from 10 power minus 3 till 10 power minus 24. I had given you varied examples earlier about these minute signals which are available in nature. So anyhow, we need not bother about the pre-amplifier conditions, where for our any pre-amplifier circuits, the input signal always will be in a very minute quantity. Anyhow, at the end of this course, in the 5th module, we are going to discuss even the large signal amplification, where we are going to discuss how the Q point will be affected by the larger signals. But as of now, it is not necessary, because we are basically discussing about an amplifier which is going to amplify the very small signals, and we will be getting a slightly larger signal at the output. That is called as small signal operation. Introduction, you already know Shockley's equation. Anyway, I will repeat for you because you should remember this. ID equals IDSS into 1 minus VGS by VP whole squared. That is Shockley's equation. The change in drain current that will result from a change in gate to source voltage can be determined using the transconductance factor in the following manner. I had briefly told you about the transconductance in one of the previous classes. As we have beta in BJT, we should also obtain some other parameter in JFET. Now, beta was a relationship between output current and input current in BJT. As in JFET there is no input current at all, we should find out the relationship between output current and input voltage. Now, if it is between output current and input voltage, then that will be ID divided by VGS. That ID by VGS is nothing but conductance, because current by voltage is conductance. As you already know, voltage by current is resistance, so current by voltage is conductance. When current by voltage is conductance, now this is the relationship between output current and input voltage. That means there is a transfer happening there. There is a transfer happening between input and output. That is what is called as a transconductance. Okay. It is given a strange symbol called GM. Now this GM is not an English symbol. As you already know, most of the inventions of the present technology happened during First World War and Second World War, and maximum of these inventions happened at that time, unfortunately, for the sake of killing. Unfortunately, most of the technical things were invented just for the sake of remotely killing the enemies. And during Second World War, all these research activities are heavily funded by the respective governments. So, at that time, the highest technical research was happening in the European countries, and Germany, France, Sweden, Belgium, Norway, Holland, Spain, they were all heavily involved in engineering research and technical research to find out the new methods of taking control over natural laws or taking control over the situation. Even now, for that matter, even now, European and Chinese people are involved in heavy research. Now at present, Indians are gradually picking up a momentum to some extent, we can say. Otherwise, it is Chinese, Japanese, Russians and Europeans who have been involved in technical research right from the last 2 or 3 centuries. So this GM is not an English symbol, it is some other language symbol. So you don't have to worry about how this G stands for what, M stands for what. Okay, it has no English counterpart because this research had happened in Europe. They had used the local language symbols at that time. So delta ID equals GM into delta VGS. We can say the rate of change of output current is going to happen when there is a slight rate of change of gate to source voltage, but the relationship between them can be related by means of a factor called GM, and this particular transconductance factor can be obtained from the transition curve itself, okay, or the transfer curve itself. This transconductance can be obtained from the transfer curve itself. That we will see how we are going to obtain it in the next slides. The prefix trans in the terminology applied to GM reveals that it establishes a relationship between an output and an input quantity. Now G is conductance, M is mutual. Somehow we are going to relate it this way. R is resistance, G is conductance. And when we write M, we write mutual. Okay. So that way, now you can remember this GM as mutual conductance. G is the symbol given for conductance. Again, don't ask me why G is the given symbol for conductance. Why not C? Because C, first letter is conductance. As I told you, this symbol is not an English symbol, but we are relating it this way. That's all. That GM is basically not an English symbol. G itself was not an English symbol. We keep on using right from alpha, beta, gamma, delta, theta, zeta, eta, iota, kappa, like that, omega. We keep on using all the Greek alphabets in our engineering sciences. Most of them are not at all English, but we still keep on using. Even today for resistance, we keep on calling it as ohms, but we write a symbol of omega there. This has been a convention from the beginning. So we keep on calling it as transconductance only or GM only in the short form. We will not be calling it as mutual conductance. Okay. Now just because I was telling you about resistance and conductance, I just want to give you a small work now. By the end of the class, any of you who are seriously listening to this lecture, by the end of the class, you give me the names for the reciprocal of capacitance, reciprocal of inductance, reciprocal of reactance, and reciprocal of impedance. Let me see how many answer. You know that the reciprocal of resistance is conductance. Similarly, what is the reciprocal of capacitance? What is the reciprocal of inductance? What is the reciprocal of reactance? And what is the reciprocal of impedance? You can put the answers in the chat box. By the end of the class, let me see how many people have answered to my question. This is only for the sake of the curiosity and for the sake that you should be knowing these basics as such. Okay. Let me proceed with the discussion now. So GM, we can write it as GM equals delta ID by delta VGS. The ratio of rate of change of drain current to the ratio of rate of change of VGS. We cannot write it directly as ID by VGS. Why? We cannot directly write it as ID by VGS. The reason is, then we are going to discuss a DC quantity. And this ID is DC, VGS is DC at the Q point. Is it so? We should write it as IDQ and VGSQ then. But that becomes a DC quantity. what we are interested in is, we are interested in analyzing JFET in terms of the AC. We need a AC quantity now, not a DC quantity. That is why when we were discussing BJT, I had told you about 2 beta. One is beta DC, one is beta AC. But I had also told that at the middle of the Q point, at the middle of the load line or at the Q point, almost beta DC is equal to beta AC. That assumption we can safely make there. That is when I had told that beta AC can be taken as beta DC itself, and we had used that beta DC itself in all our calculations. But in JFET there is no beta at all now, right? We want an AC quantity now. So GM has to be delta I by delta VGS only, which is around the Q point there. It is not a DC quantity, so we cannot directly write it as ID by VGS, because in the transfer curve the slopes keep changing. You already visualize the transfer curve. In the transfer curve, the slopes keep changing at every instant. That is when we have to find out GM at a particular point in the transfer curve, and we have to specifically define it as delta ID by delta VGS. Now, how do we determine this GM? Let us see. We can easily determine GM using graphical methods. As we have been using graphical method earlier for DC analysis as well, we can go for the same now also. Let us see how. GM is the slope of the characteristics at the point of operation, because it is nothing but delta ID by delta VGS. Y-axis is ID, x-axis is VGS in the transfer curve. You can see now, y-axis is ID, x-axis is VGS, and this is the transfer curve. If the Q point is here, we can slightly measure the slope of this transfer curve around the Q point, and we can say this as delta ID by delta VGS. That means GM is the slope at Q point, or the transconductance of a JFET is the slope of the transfer curve at the Q point. So we can graphically determine this. So GM equals M there. What is the symbol M? M stands for slope itself, right? Y equals M into X plus C means that M is nothing but the slope of the line. So M is equal to delta Y by delta X, or is nothing but delta ID by delta VGS. The slope, and therefore GM, increase as we progress from VP to IDSS. Now, from VP gradually when we move on, you can see here that x-axis will be larger, y-axis will be smaller. When you gradually move up, at some point they may become equal. Afterwards, y-axis will be larger and x-axis will be smaller. Which means what? The slope is going to progress. That means the value of GM is actually going to increase if you start from VP till IDSS along the transfer curve. But our point of interest is the Q point itself. We are not interested in taking the slope elsewhere. We are interested in taking the slope of the transfer curve at the Q point itself, because that is where we are operating the JFET. Otherwise, there can be serious errors now, because GM will keep changing from VP till IDSS. As VGS approaches 0 volts, the magnitude of GM increases. When VGS approaches 0 volts, that is when GM will have a maximum value. That is because the slope of this transfer curve will be maximum. Now let us see an exercise where you will understand more about GM. Determine the magnitude of GM for a JFET with IDSS equals 8 milliampere, VP equals -4 at the following DC bias points. VGS equals -0.5 volts, VGS equals -1.5 volts, VGS equals -2.5 volts. You already know how to plot the transfer curve. I will not ask you to do it now, because we have already done such exercises in the beginning earlier. So I will directly show you the curve now. Now this is the curve. IDSS is 8 milliampere and VP is -4 volts, and we can plot the transfer curve in this manner. Now he is asking to find out the transconductance at VGS equals minus 0.5 and VGS equals minus 1.5 and VGS equals minus 2.5. You can see this picture when VGS equals minus 0.5, when it is nearer to the origin, you can see this delta ID by delta VGS. We can simply extend this point slightly up and slightly down in equal quantity. For example, let us say we go 1 centimeter up here, we can come 1 centimeter down here. Then we can have a parallel line to x-axis and a parallel line to y-axis. We can join them. When we join them, we can find out the magnitude of y and magnitude of x. That y by x is going to be gm. So, you can see here, when VGS is minus 0.5 volts, we get delta y is equal to around 2.1 milliampere and delta x is equal to 0.6 volts. So, here the slope is 2.1 milli divided by 0.6. Now, when we come to the middle of the transfer curve, here also maybe 1 centimeter up and 1 centimeter down, that way the line can be extended and then parallel to x-axis and parallel to y-axis two lines can be drawn, and here we get 1.8 milliampere divided by 0.7 volts. Now, as the third case, when VGS is minus 2.5 volts, again from the point 1 centimeter up and 1 centimeter down, then connect them through x-axis and y-axis, we will get 1.5 milliampere divided by 1 volts. So, you can see that in the first case, when VGS equals minus 0.5 volts, slope is larger. And in the last case, when VGS equals minus 2.5 volts, the slope is lesser. You can see here that the x-axis value is larger and y-axis value is lesser. Whereas in the first case, x-axis value is lesser and y-axis value is larger. So, we can find out ID is given as 8 milliampere into 1 minus VGS by minus 4 volt whole square. This is applying the shockless equation. Now, for the first case, GM equals 3.5 millisiemens. We know that the unit for conductance is Siemens, as the unit for resistance is ohms. For the second case, GM is 2.57 millisiemens, and for the third case, GM is 1.5 millisiemens. That means you can see that the slope is largest when VGS is minimum and the slope is smallest when the VGS is maximum. In between them, the slope will have a value of around 2.57 millisiemens. If at all we consider this midpoint as the Q point, then the transconductance there is going to be 2.57 millisiemens. Now, you may wonder, why are we doing this exercise? Why are we calculating GM at different points? The reason is, for performing small signal analysis, we need a relationship between output and input, and that is why we are doing all these exercises, and these are really important. Let me proceed. Let me see, anybody has put the answer in the chat box? No, not yet. You all must be asking Googleshwar now, right? Let me see. Yeah.
So impedance we have learnt, it is admittance, but remaining we didn't learn.
Fine. Impedance, the reciprocal of impedance is admittance. Good. You are remembering that. You all learnt it from your teachers, right?
Yes,
Now, yeah. Now I'll tell you, everything you will not learn from your teachers always.
Sir, for capacitance, is it elastance?
Capacitance, it is elastance. Fine. Very good. Very good. Now you have to tell me the other two, for inductance and for reactance. Anyway, I will wait for those two answers. Meanwhile, I will tell you one small subhashita. Acharyat padamadatte padam shishyah swamedhaya padam sabrahmacharibhyah padam kalakramena cha. This is told in Sanskrita. Means, from the teacher you will learn only 25%, and remaining 25% you will learn on your own by means of your own intellectual abilities. The remaining 25% you will learn by having a group discussion along with your classmates. The remaining 25% will be learned by you as time progresses. So, don't expect that you will learn everything from teacher always. Because if you have to learn everything from teachers, then you will have to be in touch with the teachers always. But that is not the case. In a week, a teacher will be taking a class around for about 4 hours or 5 hours. That means don't expect that in 4 hours or 5 hours, whatever the teacher is knowing, you will be knowing everything out of it. The teacher will be discussing whatever is relevant for the particular course or particular topic. That's all. So, next time when I ask you this question, don't say that we have learned only about impedance. I am asking you to learn something on your own now. And you have enough resources to learn all these things to find out. Let me see. If you don't give the answer, then I have the answer. Don't worry. I'll tell you the answer at the end of the class. Fine. Let me continue now with the discussion of transconductance. Let us see what is the mathematical definition of GM now. This will be slightly complicated. We have seen already that the graphical definition is easier to arrive at, whereas the mathematical definition is slightly difficult, that we had seen in the DC analysis also. But still, for the sake of theoretical importance, let us find out in what way we can define the transconductance mathematically. The derivative of a function at a point is equal to the slope of the tangent line drawn at that point. Now, if you relate calculus with geometry, you will always come to know that in geometry, whatever you call it as a slope, in calculus, that itself is the derivative of that particular function. So now, we will use the same thing here now. The derivative of a function is nothing but the slope. That we will see. That is the relationship in which geometry and calculus are related. Now, GM is, instead of delta ID by delta VGS, let us write it as dID by dVGS. Differentiation of drain current with respect to VGS, or the rate of change of drain current with respect to that in VGS. Now, it is especially with respect to Q point. You can see this. We are not interested in finding out the transconductance at the far ends of the transfer curve. We want to find out the transconductance at the middle of the transfer curve, because that is where you are operating the switch. So, it is at the Q point. Now, for ID, we will substitute Shockley's equation. ID is IDSS into 1 minus VGS by VP whole squared. Now, we will differentiate Shockley's equation with respect to VGS. Now, we know that IDSS is a constant. Take the constant out and differentiate 1 minus VGS by VP whole squared with respect to VGS. Now, you already know the differentiation of this particular term inside 1 minus VGS by VP whole square or 1 minus X whole square. That is 2 into IDSS into 1 minus VGS by VP into differentiation of again 1 minus VGS by VP. Okay. So, this is nothing but 2 IDSS into 1 minus VGS by VP into differentiation of 1 minus 1 by VP into differentiation of VGS itself. Now, you know that the differentiation of a constant is always 0, and you already know that VP is also a constant. Pinch off voltage and saturation current are constants. So, finally, we get this expression 2 IDSS into 1 minus VGS by VP into 0 minus 1 by VP, or we can express GM as 2 IDSS divided by mod of VP into 1 minus VGS by VP, because this 1 minus VGS by VP is a factor which we obtained here. Now, the 0 minus 1 by VP, we need not have a minus sign here. If at all we take this minus sign, transconductance will have a minus sign. We need not have a minus sign. Why? Resistance cannot be negative. Conductance cannot be negative. Capacitance cannot be negative. Okay, inductance cannot be negative. Impedance cannot be negative, right? Admittance cannot be negative. That way. So, GM cannot be negative. Why should we unnecessarily complicate by putting a minus sign? Instead, we will simply put mod of VP. 2 IDSS divided by mod of VP into 1 minus VGS by VP. Now, you will have to remember this expression. Just like you have remembered the Shockley's equation For the small signal analysis, you will have to remember this expression, which is a mathematical expression for the transconductance. So, I will repeat it 3 times now. Gm equals 2 IDSS by Vp into 1 minus Vgs by Vp. Second time, Gm equals 2 IDSS by Vp into 1 minus Vgs by Vp. Third and the last time, Gm equals 2 IDSS by Vp into 1 minus Vgs by Vp. Now even I will also remember, even you will also have to remember. Let me proceed now. This is the mathematical definition of the transconductance. Plugging in Vgs equals 0 into the above equation, what we get? We get the maximum value for Gm, because we know that when Vgs is approaching to 0, we will have a maximum slope. So then Gm equals 2 IDSS by Vp into 1 minus Vgs by Vp, where Vgs is 0. So we get Gm 0 equals 2 IDSS by Vp. See, now we are giving a symbol Gm 0. What does it mean? Gm 0 means the transconductance when input voltage is 0. And that is when the slope will be maximum. So even this Gm0 will be useful for us in future for our exercises in the small signal model. Let us see that later on. We are specifically giving a symbol Gm0 now, that is 2 IDSS by Vp, where the added subscript 0 indicates the value of Gm when Vgs equals 0 volts. Now Gm equals Gm0 into 1 minus Vgs by Vp. Look at this. This 2 IDSS by Vp is given a symbol now Gm0. And now we can rewrite Gm in terms of Gm0 into 1 minus Vgs by Vp. Now look at the beauty. If at all we get this Gm0, then we can easily find out Gm at any VGS. See, manufacturer will be giving us IDSS. Manufacturer will be giving us Vp. So we can immediately find out Gm0. Once we find out Gm0, for any value of VGS, we can simply substitute Gm equals Gm0 into 1 minus Vgs by Vp. That way, when we know the Q points VGS we will be knowing, we can easily deduce the transconductance at that point. That is why I told you, you should remember Gm0 also, which is going to be useful for us. In the equation form, Gm equals GFS equals YFS. We are going to discuss some parameters called hybrid parameters in the third module. I had briefly mentioned you about it, and I had told you in the first module that beta is also called as HFE, where H stands for hybrid, F stands for forward, E stands for emitter, which simply means that it is for the common emitter configuration. Same way here also, we can write Gm in some other form as GFS or YFS, where F signifies the forward transfer conductance and S indicates that it is connected to the source terminal. For JFET, GFS ranges from 1 millisiemens till 5 millisiemens. In general, they have measured the values of transconductance for JFET. It can be different for MOSFETs as such. Here now we are discussing only JFETs. So the transconductance for a JFET typically ranges from 1 millisiemens till 5 millisiemens. You don't have to worry too much about these terminologies. There is another equivalent term called YFS, another term called GFS. It is simply a notation that forward and source, if it is a common source configuration. Otherwise, in general, we always refer it to GM. The thing here is, in engineering sciences, there are a lot of notations available because there have been a lot of engineers and scientists working in this domain since last 2 or 3 centuries. So there can be many notations. That is one reason. Another reason is, whatever engineers talk or whatever symbols engineers use, only the other engineers will understand and only the other engineers will come to know. It should not be for the common public. A common public may not understand anything out of these discussions. So maybe to some extent, we engineers want to use many types of symbols so that only we will know them, no one else will know them. That may also be a factor. Just like medical doctors use lot of abbreviations for their own methods or medicines or therapies or whatever. Only the related people will understand whatever a medical doctor has written on a prescription or on a diagnosis sheet. Others may not be understanding. Many times a patient himself or herself may not be understanding whatever terminology medical doctor is using. It's the same case with engineering sciences also. So you don't have to worry too much about whether we are going to use all these symbols in our discussions elaborately. We will be predominantly using only GM, because we will be predominantly working with only common source amplifier as such. You might have observed that in the DC analysis, we discussed about common source amplifier and we discussed about common gate configuration. We did not discuss much about common drain configuration, because it is as similar to common collector configuration in case of VGT, and there is no point in discussing those things again and again. That common collector configuration itself, we had called it as emitter follower, in the case of which the voltage gain was unity. In the same way, even for a common drain configuration, it is called source follower, and there the voltage gain is going to be unity. So as they are of similar approach, there is no need to discuss them again and again. That was the point there. Now, let us have an exercise before ending. I am unable to see this. Okay, now I am able to see. Again it came. That upper portion is coming again and again. Okay, it went now. Exercise 2. For the JFET having transfer characteristics of exercise 1, find the maximum value of GM, the value of GM at each operating point. The maximum value of GM can be easily found out that itself is GM0. That can be easily found out, and the value of GM at each operating point. Let me show you the solution. GM0 itself is the maximum possible value of GM, that is 2 IDSS by Vp, that is 2 into 8 milliampere 4 volts, that is 4 millisiemens. At VGS equals minus 0.5 volts, we can substitute the value with this equation. GM equals GM0 into 1 minus VGS by Vp. Substitute VGS as minus 0.5 volts, you will get 3.5 millisiemens. In graphical form also we got it approximately same. But in the graphical form there can be errors. The mathematical form is now much more accurate, as you already know. At VGS equals minus 1.5 volts, GM equals GM0 into 1 minus, again minus 1.5 by minus 4 is 2.5 millisiemens. Graphically we had got 2.57 millisiemens there, because there that y and x values cannot be taken to 2 decimal points, because it is a graphical point. There can be only 1 decimal point. That is when we get around 2.57 millisiemens there. This 2.5 millisiemens itself is the accurate value there. Now lastly, at VGS equals minus 2.5 volts, GM equals GM0 into 1 minus VGS by Vp. Substituting minus 2.5 volts, we get GM equals 1.5 millisiemens. In graphical form also we got the same answer. Okay, this is how we can find out the maximum value of transconductance, that is 2 IDSS by Vp. We denote with the symbol GM0, and we can simply substitute GM equals GM0 into 1 minus VGS by Vp. That is one way, or else you can always remember the formula for GM0 is 2 IDSS by Vp. So you can always remember GM equals 2 IDSS by Vp into 1 minus VGS by Vp. That is going to be the standard formula for transconductance. Now my students have not yet given me the answer. Okay, I will give you time till next class. In the next class, you will give me the answer correctly for the reciprocal of all those 5 things systematically. That means resistance, capacitance, inductance, reactance, impedance. Now you already know that 1 over R is conductance and 1 over Z is admittance. Impedance is Z, admittance is Y. That is the symbol given. That is why here also for that GM, symbol GFS was given and YFS was also given. Y is the symbol given for admittance, because Z is the symbol given for impedance. Similarly, R is the symbol given for resistance and G is the symbol given for conductance. Now, similarly, for capacitance, inductance and reactance, 1 over of capacitance is what? 1 over of inductance is what? And 1 over of reactance is what? You find out, and in the next class, you tell me the answer. Until then, take care and bye-bye.